Okay, welcome to our lesson on arithmetic sequences. So we looked at sequences and recursion last lesson. It was a pretty simple, nice little introduction into the topic. Now we're particularly going to be looking at arithmetic sequences. What are they? So a sequence where each term can be found by adding the same number each time. So it's really similar to what we did yesterday, but an arithmetic sequence in particular is when you're only adding. So you're adding the same number every single time to get the next term. So an example there is 8, 13, 18, 23, and 28. So thinking about what you're adding there, you're adding 5. 8 to 13 is 5, plus another 5 to get to 18, another 5 to get to 23, or the next example, 26, 24, 22. You're still adding, but you're adding a negative number. So the same as minusing. So 26 add negative 2 is 24, again 22, 20, and 18. And notice, because we add the same number each time, the difference between all the terms is the same. So in the top example, there's a 5-unit difference between 8 and 13, and there's a 5-unit difference between 13 and 18. And so the difference, we call that the common difference, because it's the same each time. So that's one important thing you'd probably want to note down for arithmetic sequences, that they have a common difference. So we looked at recursion yesterday. So what we're going to do now is use recursion to generate an arithmetic sequence. It's a 2-part process. So the first part is getting the first term of the sequence, and we call the first term T1. So you write that little 1 next to the T. So T1 is equal to A. We don't know what the first term of the sequence is. We don't even have any numbers in front of us, so I'm just going to call it A. And then successively adding the common difference D, so we call the common difference little d, to each term to obtain the next. So there are 2 parts to the process. You get the first term, and then you add the common difference to get each term individually as you go. So for example, if we had to write the rule for the recursion to this sequence, 10, 15, 20, 25, in words we would write, well, the first part of the process is start with 10. And then the second part of the process, to get the next term, add 5 to the current term and repeat the process. That's a pretty easy one to see. You're just adding 5 each time. Again, mathematicians are lazy. We don't want to have to write out sentences every single time we do recursion for an arithmetic sequence. So we want to use little symbols, little shorthand things that make our lives quicker and easier. Okay. So let's think of each term in the sequence as something to do with T. So the first term is T1, the second one's T2, T3, T4, and so on. We don't know when the sequence stops, so we're just going to say Tn. So we're going to denote the last number in any sequence as Tn, so that's the nth term. So from the previous example in our 10, 15, 20, 25, looking over here, there it is, the 10, 15, 20, 25. Our first term, our T1, so the little 1 next to the T, is 10. Our T2 is 15. T3 is 20. T4 is 25, and so on. And using that notation, we could generalize for any arithmetic sequence recursion. So even if we didn't know the numbers. So T1, let's just call it A. We don't know what it is. We don't have any numbers in front of us. I'm just going to call it A. And then Tn plus 1. So let's have a think of what that means. N just indicates the term that you're on at the moment. So Tn plus 1 means the one after the term that you're on at the moment. So to get Tn plus 1, you take the term that you're on at the moment, Tn, and plus the common difference, because if we add the common difference to the thing that we're currently on, we'll get the value of the next thing. So that there is our general notation. If we don't have any numbers, that's the notation we use for writing an arithmetic sequence in general. At this point, I would pause the video and copy that down as well. So this here is important. This is called a recurrence relation. So the recurrence relation is that little bit there that you just copied down. We can use the recurrence relation to test whether a sequence is arithmetic. So you might get a question that says, here's a sequence, is it arithmetic? So you can use that recurrence relation to tell me whether the sequence in front of you is arithmetic. And it really is just kind of a rearrangement of the relation. So Tn plus 1, so keeping in mind that means one more than the one you're currently on, minus the one you're currently on, should give you the common difference of D. And that makes sense. In the example that we had above, 10, 15, 20, 25, let's just say the current term that you're sitting on is 15, and you want to test whether this sequence that we've got in front of us is arithmetic. We know it is because we just went through it, but say if we didn't know, we want to test if it's arithmetic. We would go, okay, Tn plus 1 minus Tn is equal to the common difference D. That should be true if this is arithmetic. So 20 would be the one more than what we're on. 15 is the one we're currently on, and that gets us to 5. Yep, cool, 5 is our common difference, so I know it's arithmetic. It's a pretty logical process when you think about it. So let's have a go at an example. An arithmetic sequence is defined by the recurrence relation. T1 is 4, Tn plus 1 is Tn minus 2. So the first term, T1, is 4. And to get all of the other terms, you're going to take the one that you're on and minus 2 to get the next one. So thinking about that, if you're minusing off a number, you would assume that your arithmetic sequence should be getting smaller for every individual term that you add. That makes sense. So let's have a go. The first 6 terms, our first one is 4. Comma, we always have to put commas. To get the next one, so to get one more than the one I'm currently on, I take the one I'm currently on and minus 2. So 4 minus 2 is 2. 2 minus 2 then is 0. 0 minus 2 is negative 2. Negative 2 minus 2 is negative 4. And negative 4 minus 2 is negative 6. And the question only asks for the first 6 terms. I'm going to assume that this goes on indefinitely. We haven't been told otherwise. But the first 6 terms are those ones. All right, pause the video, guys, and have a go at this one. T1 is 12, and the recurrence relation is Tn plus 1 is equal to Tn plus 8. So writing the first 4 terms. When you're done, jump back on the video and check that you got the solution right. So you should have had your first term as 12. Second term, 12 plus 8 is 20. Oh. 28, so we're adding 8 each time. 36, how many is that? We want the first 4 terms, so that's all. 12, 20, 28, 36. I'm going to indicate that this keeps going with an ellipsis. And that's how you generate an arithmetic sequence using your recurrence relation. So not too tricky. The next thing I want to go through is graphing then an arithmetic sequence. Again, not super confusing. We're just going to take our sequence of numbers and pop them on a graph. It's just a visual depiction of the sequence. So sometimes looking at numbers in a line with commas between them doesn't really tell you very much. In fact, it often doesn't tell you much. It's not until you make a picture or a visual out of those numbers that you can actually make sense of what's happening. One thing to keep in mind when you're graphing an arithmetic sequence, it's going to tell you a lot about whether your sequence is growing or whether it's decaying. And they're the two terminologies that we use with arithmetic sequences. So if your sequence is getting bigger, so you're adding a positive number each time, that's your common difference, you would assume that your graph will be going up. And that's a growth. So that's a growth. If you're adding a negative number, minusing a number off every single time, you would assume that your graph's going to go down. So that means you've got a decay. So when something's decaying, it's getting smaller, or it's decreasing. So that would be a decay. So in the case that something's got a positive increase, you'll see a growth. and a decrease is a decay. All right, so let's have a look. So writing these sequences in a table. So the ones up above, if T1 is 22 and the recurrence relation is Tn plus 1 is equal to Tn plus 2, the answers are already in there. So we've got T1 was 22, T2 is 24, and we add 2 each time. T3 is 26, T4 is 28, and T5 is 30. I should have rubbed these out before we started. So graphing that, let's have a look. As a graph, this is going to look like my first term, I go and put a little dot at 22. Second term is 24. Third term, 26. Fourth term is 28, and the fifth is 30. So you can see a linear growth there. It's going up by the same thing each time, so you would expect it to be linear, which means you've probably done the question right. And that's a growth, like we spoke about before. The next one I'd like you guys to do. So I've put your sequence in a table already. 18, 16, 14, 12, and 10. And I would like you guys to write that as a graph. So at this point, pause your video and go and write those ones as a graph. This is what you should have got. So your first term, so when n is equal to 1, you've got 18, and then it goes down by 2 each time, 16, 14, 12, and 10. Again, linear, what you would expect. It's going down, so we call that one a decay. We've already been through this. What do you notice about the shape of the graphs in each situation? It's all pretty logical. The numbers are going down, you're going to see a decay. Numbers are going up, you're going to see a growth. Okay, guys, questions for this lesson are exercise 4B. Have a go at them all. Have fun.